Thank you very much, and thank you very much for this opportunity to speak here. So I'll be giving 2 talks in the morning and 1 talk in the afternoon. The talk in the afternoon will be more geared towards research. And in these 2 hours, I would like to give more of an introductory talk about random graphs. The kind of models that are being considered in the literature, the kind of applications that we're having in mind. So random graphs are used to model real-world networks. So what kind of networks are these and what are their properties? And I will also say something about distances in such random graphs. And this is related to the paradigm of 6 degrees of separation. So just as a check for me, who knows about random graphs? A little bit. Okay. Who knows about branching processes? Okay, so I will not assume that you do. All right, so this is the plan of the lecture. I will talk about real-world networks and random graph models for them in my first lecture, which will probably last a bit longer than an hour. And then in my second lecture, I will talk about small world properties in these random graphs. How do distances behave? And the material that I will be presenting come from lecture notes in preparation. These are the links. They're on my website. They're in preparation already since quite a while. I've been working on them for 7 or 8 years. And I'm now finally planning to complete the first part, which will be chapters 1 and 2, 8. I'm writing here the slides are available. They're not there yet, but I'll put them there. But I will also give the slides to Moes so that you can have a look at them. In my talks, the arguments will be probabilistic. I will be using branching process approximations, and I will be using first and second moment methods. So I will not be focusing a great deal on proofs, but I hope to shed a little bit of light on some of the ideas that are behind the material. So, real-world networks. Here are 2 examples of complex networks. So, this here is the protein interaction network of yeast. There are about 11,000 proteins in yeast cells, and they interact in a very complicated way, in a very complex way. So every node here is one particular protein, and you connect 2 proteins to one another when they interact in one way or another. So it could be that there is a chemical reaction in which one is turned into the other. Or it could be that there is a chemical reaction in which the 2 of them are combined to a third. Or one could be an enzyme or a catalyst for a reaction in which the second takes place. So the meaning of these edges could be very diverse. And of course, as you can imagine, just producing a picture like this takes many years of research in biology to actually find out what all of the biological pathways are that exist within a yeast cell. And this is just a picture. It's a very famous picture appearing for the first time in a paper by Albert and Barabasi, and it was one of the first examples of a complex network. Now, this is an artist impression of the internet topology in 2001. So this is a completely different field, but somehow the pictures are a bit alike. Now, in the internet, the vertices are routers, so real computers, and 2 computers are connected. 2 routers are connected by an edge in this picture when they're connected by a physical cable. So this really is a physical network of computers connected to one another. Now there's some confusion. Some people also call the World Wide Web internet. It isn't. The World Wide Web really is a different thing. It's also a complex network, but the World Wide Web has different properties. First of all, it's much larger because the World Wide Web has as vertices the web pages that are around, and it's actually not even clear how many web pages there are. Maybe 1 trillion, maybe 10 trillion or something like that. And actually nobody knows, even Google, who actually has the largest resources for knowing which web pages are around, it's estimated that they only have a coverage of about 30%. So there's a lot out there in the World Wide Web that we don't know anything about. Whereas the internet we know. So the internet is completely different. For one thing, the internet is connected, because the internet supports email. So if it would not be connected, then you would have a problem. And one part of the network could not send messages to the other part of the network, and that's something that we don't want. In the World Wide Web, there's no reason why the thing would be connected. So just to make it very clear, in the World Wide Web, the vertices of the network are web pages, and you connect two web pages to one another by a directed link when the first links to the other, or has a hyperlink to the other page. So this is a completely virtual network. It's much larger and completely different, but it's still a complex network. Now you may wonder why we're studying these networks somehow from an abstract point of view, because all of these networks are completely different. And in a certain sense, of course, they are. Every network has an origin, and that origin is studied in a particular field of science. Right? Biological networks are studied in biology. Economical networks are studied in economics. Social networks are studied by social scientists, and they've been doing that for a very long time. So all these different networks have different origins. But the peculiar thing is that they share lots of commonalities. And that's what I would like to focus on. So here we again see a picture of the internet. It's a different way of visualizing the internet because it's on the autonomous systems level. So in the autonomous system, you conglomerate lots of routers that are operated by the same operator. So for example, Imperial College would be considered an operating system, and it would be glued together, and all of the outside links would be merged. And then you, of course, get a slightly smaller graph. So the internet as by itself is about 200 or 300,000 routers, whereas the autonomous system graph is somewhere in between 11 or 20,000. So it's a bit smaller. And this is another example of a complex network, and that's the Internet Movie Database. So the Internet Movie Database is an example of a social network in which the vertices are actors, and you connect two actors to one another when they've played in the same movie. So it's a collaboration network. In fact, you can do the same thing for scientists, and then you would connect two scientists when they've collaborated on a paper. Also, that is a collaboration network. So this is something like a social network, or it's a reflection of social dynamics that is taking place. And therefore, you may think that this is a completely different network altogether again. Now, one of the things that is special about these networks is that there's a high amount of variability in the number of connections that the individuals within the network make. So mathematically speaking, that is about the degree. So you have a vertex, it has a number of neighbors. In the social context, these would be friends. In the internet, these would be the routers to which the router you're looking at are connected to. And in the Internet Movie Database, it would be the actors that you've collaborated with if you're an actor. And the question is, how many do you have? Well, that means that for every node in the graph, every vertex in the graph has a degree, and that's some number ranging from 0 to I don't know where, to the maximal degree in the network. And of course, it is possible that these degrees don't vary a lot, but what we see in real-world applications is that they do vary a lot. So, for example, in an Internet Movie Database, it's difficult to read, but the degrees go from 10 to the power 1 to 10 to the power 4. So that means that there are actors that have collaborated with other actors with 10 to the power 4 other actors. That's actually quite a lot. Huh? And so this is sometimes called scale-free. And scale-free is a bit of a dubious term. It's actually not entirely clear what it means. The physicists mean that there is a power law in the background. So power law would mean that if you look at this in a log-log scale, which is typically how we plot these pictures, then you would get something which looks like a straight line. And then the slope would be minus the power in the power law degree sequence. So if you see things that in a log-log plot look like a straight line, then you should think of power laws. Now there's a lot of debate as to whether there really are power laws, and I'm not going to settle that debate for you. But what is clear from the pictures is that there is a high amount of variability. So here you see this 10 to the power 4, but actually because this is a log-log scale, if you go down a little bit, the numbers drop significantly. Right? So the majority of actors actually is somewhere here. And that means up to maybe degree 20 or 30. So probably if you take the average degree, you get a number that might be 30 or 35 or so, but that actually doesn't convey the whole message here. Because what we tend to think about is things that are well concentrated. So you have an average, and then the majority is not so far away from that average. Think about height of people. In the Netherlands, the average height of a Dutch male individual is 184 nowadays. Meters. I'm in the metric system. Don't ask me to translate this. I won't. So it's 184 in the Netherlands. If you add 20 centimeters on both sides, you have the majority of the Dutch male population. It's in between 164 and 204. There are, of course, people who are taller or smaller than that, but the majority really is there. And 20 centimeters compared to 184 is actually not a great deal. So that's, I mean, many properties are like that. You have an average value, and there is fluctuations around that average value, but it's not a great deal. This is not like that. And another example, which is very different in terms of the amount of fluctuations, are incomes of people. This is actually how these power laws came about. Pareto was thinking about incomes of people, and he was realizing that a large part of society, or a large part of the wealth in a society, is owned by a very small proportion of individuals. Now, this is typically what you see in power law behavior. And again, if I translate that to the Dutch context, the average income is probably somewhere between 20 and 30,000 euros. Now suppose you add 10 or even 20,000 euros, add and subtract 20,000 euros to that, there's still a sizable amount of people that you're missing out on. Right? In fact, there are several orders of magnitude that you can be, that your income can be higher, and it's still, I mean, it would be a lot. If you go from 20 to 200,000, 200,000 really is a lot. But still, there are quite a few people who actually earn 200,000, and there's even a much smaller amount of people that earn 2 million. So you should really think of orders in magnitude. So this is log-log scale, right? If you're multiplying by a constant number a couple of times, this is log-log scale. So there's no typical scale, and that's what I mean with scale-free. You can, of course, translate that in a mathematical way, in a mathematical model, by saying that there is a power law, but this is not necessary. What I just mean is that there is a high amount of fluctuations. And you see that in these pictures. Now, of course, this is a bit dubious because the graph is not very large, so drawing a straight line to that, okay. Here, I haven't drawn the straight line through it. This actually comes from a very famous paper by the Falutsos brothers, Falutsos, and Falutsos. And it's quite charming because they actually thank their mother in the paper, which I think is very nice. But this paper received a lot of criticism because, well, first of all, the data set was not very large, and actually they took the data from another source, and that other source was warning for the amount of errors that was in the data, and they just ignored those completely and just did analysis on it. But it attracted a lot of attention because it was somehow in the right moment of time. Some things come in the right moment of time, and people were thinking about power laws. They saw these pictures and say, okay, internet also is scale-free. All right. So that's one of the things that many of these networks have in common. Another thing that many of these networks have in common is that they tend to be small worlds. So a small world, that's a phrase that we use very often. It comes from a Disney movie. It's a small world after all. But it also refers to, I mean, you meet somebody that you've never talked to, you exchange some information, you get to know that the person is working at a place, and you ask, do you then maybe know this or that person? And the person knows. And then you say, well, it's a small world, right? So after a short communication, you're able to find a common friend. That's actually quite remarkable if you think about it, right? I mean, we're talking about millions of people. And why is it so that you after a very short discussion, you're able to find a common friend? So this is one aspect of a small world. Another aspect is 6 degrees of separation, which is the paradigm that states that if you take two individuals on this planet, you're able to find a path that links them with at most 6 people in between. So it's a small world. Now, of course, you could postulate this, and this was done by a Hungarian in the 30s, but it was very difficult to check. So it's only with virtual networks, like the internet, but also the Internet Movie Database, and Facebook, and these kind of graphs, that you could actually check whether this is the case. So here are 2 examples. This is a social network called gay.eu, and this is a social network called LiveJournal. And what we do is we look at all the possible pairs within the network, so this is computationally quite difficult. You look at all the pairs of nodes in the network, and you count how many hops you need to make to go from one to the other. And then you make a histogram out of that. And if you want to compare pictures, it's often a good idea to normalize. So then you get a probability distribution. And what that probability distribution does, so this here is a probability distribution, it adds up to 1. What that probability distribution describes is the probability distribution that you get if you were to draw 2 people uniformly at random from your system, from your complex network, and you would count how many hops they would be apart. And if you were to do that in this network, with probability very close to 40%, this distance would be 7. Yeah? And it can also be 6 and 5 and 8 and 9. But sort of after these values, you don't see many values anymore. This actually is a pretty large network. You should think of the order of a million. So why is it the case that these networks are so efficiently routed that you can go between vertices relatively quickly compared to the size of the network? I mean, it would not have been so strange if there would be individuals that are at least 100 hops apart. But there aren't. So that's the small world paradigm. And we see that coming back in many examples. And this is a quote that I like a lot. It comes from a movie play, 6 degrees of separation. And it says, everybody on this planet is separated only by 6 other people. 6 degrees of separation. Between us and everybody else on this planet. The President of the United States. A gondolier in Venice. It's not just the big names. It's anyone. A native in the rainforest. An Eskimo. I am bound to everyone on this planet by a trail of 6 people. It's a profound thought. And indeed, it's a profound thought. It basically means that you can go between yourself, making it very personal, and everybody else by a trail of 6 people. And that's actually a relatively short trail. Of course, the trail depends on whom you're trying to connect to, but okay. Now, this may seem a little bit strange, but what you should bear in mind is that there's individuals within the network that play a highly special role. I think the British Queen would work well in this respect. Maybe each of you can actually find a trail to the Queen, and probably this trail is not going to be very long. Do you happen to know anybody who's shaken hands with the Queen? Do you happen to know anybody who happens to know anybody? Well, okay, I already see some hands. If you happen to know these people, you're at distance 3 from the Queen. Okay? So that means if this is true for everybody, everybody is at distance 6 from one another in the UK. There you go. And that's really the way how you should think of this. That if you want to move from one person to another person, you typically tend to do that by individuals in the middle that are extremely highly connected. The Barack Obamas, the Queens, maybe the Dutch King, even though he's still relatively young. So that's the kind of phenomena that we're trying to understand in this setting. So we're trying to model this in the right way. Okay, now of course, if you're thinking about networks, nowadays everybody thinks about Facebook. And of course, Facebook really is the largest network that you can think of. Well, besides the World Wide Web maybe. But Facebook is a network that you can get your hands upon. And it is a personal network. So Facebook has somewhere around 1 billion active users. The Facebook graph, the network itself, and the network properties of it were investigated in November of 2011. And at that time, there were only 700 million active users. Still quite a lot. And in fact, this raises a lot of complications. Because if you want to do computations in a graph of size 700 million, well, this is actually not so simple. To just give an example, we actually do not know what the diameter of the Facebook graph is. Because, I mean, what is the diameter? You take the maximum overall starting and ending points of the graph distance between those. Okay? In order to know what this is, you actually have to test every starting and end point. Otherwise, you're not going to be certain. Now, we do know that the diameter is at least 59, which is large compared to 6. But we don't know what it really is. So computer scientists, and these are the people listed over there, have tried, but it's extremely difficult. So this is just computationally not feasible. But it's much easier to compute the distances within the graph because you can just do a statistical sampling. I mean, if you want to know what the distances are, it's probably sufficient to take 10,000 pairs, plot the histogram of that, and you will actually get a pretty good estimator of the true distances in the network. For the diameter, that doesn't work. But for the distances, it does. It has a much nicer statistical interpretation. Now, if you do that, and in fact, in some cases, you can even do it for the complete network, you get pictures like this. And here, the distances are even much smaller. So this is 6. And the average value is around 4. So 4 degrees of separations because of Facebook. That, of course, was a good media, that raised a lot of media attention. And here you can also see how it changes over time. They also took some smaller subgraphs. For example, they took Italy and Sweden, probably because they aren't so big. And as you can see, Italy was relatively late in adopting Facebook. In 2007, the distances were still relatively high, which means that it's actually very thinly connected. And as time proceeds, it goes more in the direction of the complete Facebook network. So also, Italy has adopted to Facebook. And one of the things you see is that these pictures are actually not very much different whether you look at Italy, Sweden, the combination of Italy and Sweden, that is green, or the US. The US, of course, is much bigger than any of those. Or entire Facebook. Entire Facebook is the most different. But if you take sort of the Facebook on a smaller scale, you still get pictures that are roughly the same as for the entire network. That's interesting, because it basically says that geometry does not play that important a role. All right, so now I would like to show some movies. And these are movies of the Internet Movie Database. The nice thing about the Internet Movie Database is that you can download all the information about all the movies, and then you can just compute at every time instance, because the movies have a timestamp, you can compute all the graph properties. And then you can compare that, how that evolves in time. And this is what happens. Oh, and this is the same thing, but then for the distances. So it starts in somewhere around 1895. And of course, at that moment, it's still an extremely small network. But very quickly, it stabilizes. And these pictures actually don't change a great deal. I mean, not from the 60s to now, despite the fact that the network actually changed dramatically. So let's show that again, because this was always very quick. Oh. Okay, so we start in the end of the 1800s. Now we're in 1920. We already see the characteristic picture that we see in 2007, which is the last plot. And it becomes more and more stable, and it thins out more and more. So you see more and more in the tails, also because you get more and more vertices in the network. But it's quite stable. You see these dots that are somehow shrinking down. So here are the distances again. And what you see is that from the 30s on, well, the picture doesn't really change a great deal. These numbers here are the number of pairs. So you should take the square root, if you can, to get the size. Yeah? So there's something interesting in this network, in the sense that the dynamics which is given by the movies that enter the system, and they describe what the actors are, the dynamics seems to be stabilizing over time. And I don't know why. I have no idea. But I find it rather fascinating. This really is a dynamical property. No. View full screen. All right. Before we go to modeling, are there any questions about these real-world networks that I've described? Yeah.
How does directionality change the scale-free topology?
Right. So the World Wide Web is directed, and there is some consensus about the fact that the in degree has obeys a power law, but the out degree is not so clear. So of course, when you have a directed network, the statistics of the in degree and the out degree could be quite different. Of course, they sum up to the same thing. The sum of the in degrees is the same as the sum of the out degrees. But apart from that, they could be entirely different. Directionality does make the problem a little bit more difficult. So for example, if you're looking at connectivity properties, how do you define that? I mean, if I look at this vertex and that vertex, it makes a difference whether I look at the direction from here to there for a path, or from there to there. It could be that this one is connected this way, but not that way. Yeah. So that raises some extra complications. This is one of the reasons why I'm actually not looking at directed graphs. But there's a lot of theory about this as well. Yes?
If you exclude a certain, say, portion of the very high degree vertices, how does that sort of alter the characteristics? Because that actually kind of relates to what that gentleman said.
Yep.
In a way,
Yep.
I can't, I
Yep.
can't always kind of...
Can I postpone that?
Yeah.
Yeah. Because once we get to the results, I can say a little bit more about that. I mean, for the real-world networks, we haven't tried. We could, but we just haven't done it. But in the models, I can tell you what the effect will be. It actually is a very good question. It's also strongly related to what is called vulnerability of these networks. So what is often referred to in vulnerability is what happens if you knock out part of the system. And you can do this in several ways. One thing you could do is just randomly knock out vertices. So this is a random attack. Or what you're having in mind is more a deliberate attack. I mean, what you would like to do is first knock out the people who are most influential. And these are probably the ones with the highest degree. Now the question is the effect of that really a lot more fierce than the effect of knocking down random individuals? And in some cases the answer is yes. In some cases it doesn't matter that much. Yeah. Any other questions? Okay. So what I'll do now is I'll introduce 3 different models for random graphs. And these are 3 different models that have attracted a lot of attention in the literature. There are tons more models. And I'll actually say a little bit about why different models are being investigated still at this time, despite the fact that we already have lots of them. But these are the ones that have attracted the most attention. These models and variations upon them. So the first is the configuration model, and it's sometimes called a random graph with a prescribed degree sequence. And it's a static model. And with static, I mean that it's a model of a fixed size. So you have a network in mind, for example, Facebook at this time, 700,000 users. I just postulate that the size of the network is 700 million, and that's it. So that's what I call static. That's one model. The second model is what are called inhomogeneous random graphs. These are adaptations of the well-known Erdős-Rényi random graph model to settings where vertices play a different role. It's also a static model, so you fix the size once and for all in the beginning. And then there's a third class of models, which are called preferential attachment models, and these are dynamic models. So in these models, the network size grows over time. So let's start with the configuration model. So the configuration model has a history, and it has a history well before the time of investigating complex networks. So the complex networks boom started with 2 papers, one by Albert and Barabasi, and another by Newman, Strogatz, and Watts. So it's all around 2000. And in fact, the configuration model was already investigated around the 80s. Bolobash was one of the first to study the configuration model because he wanted to count the number of graphs with a given degree. So he was doing it in the regular case, as it is sometimes called, where the degrees are all the same. And then there was a paper by Molloy and Reed in '95 who extended that setting and looked at graphs with varying degree. So you would just fix the degree of a vertex, do that for every vertex, and then study the properties of this particular model. And they were looking at the giant component. And it was popularized by Newman, Strogatz, and Watts, three physicists. Well, Strogatz maybe also is a mathematician. And they postulated this model as a model for real-world networks in which you know the degree sequence. And it's funny because if you look at the citations, so these are from May last year, this is a very influential paper. It has 2,000 Google Scholar citations. This for a math paper, 1,200, is a lot. You don't see that very often. Now this, of course, are also high numbers, but they're not equally high, despite the fact that this actually comes before that. So Molloy and Reed, of course, nicely referred to the paper by Bolobash and also by to the paper by Bender and Camfield. But Newman and Strogatz and Watts don't. So they will refer only to the Molloy and Reed paper. This is the reason why the Molloy and Reed paper has so many more citations. So sometimes the model is called the Molloy and Reed model, and some people are very angry about that. Okay, so what is the model? Well, as I was saying, you fix the number of vertices beforehand. So think of a few 100,000. That's n. Or a few million, if you wish. And of course, we'll do asymptotic, so later n will tend to infinity in all of my statements. And then we also fix a sequence of degrees. So you could have in mind that every vertex has the same number of friends. So that would be a regular graph. But it could also be that there is a high amount of variability. And what we would like to do is understand what the effect of this high amount of variability is on the graph properties. So if you have individuals with very high degree, you somehow believe that that should shrink the distances. Now, is that true, and can you quantify it? That's the kind of questions that we're having in mind. Now, of course, there are several ways how you can choose these degrees, and often we'll just take them IID, so they're random as well. Now, because of this scale-free phenomenon, what we'll have in mind is settings in which the number or the proportion of individuals with degree at least k falls off as k tends to infinity, because it's a probability distribution, but it falls off very slowly. And it falls off slowly as an inverse power of k. So just to compare, if you would do this for, let's say, a Poisson random variable, the drop-off would be even faster than exponential. If you do it for a Gaussian, a normal random variable, the drop-off would be like e to the power minus k squared. So this really is a lot slower. So that also means that if you draw n of those individuals uniformly at random, the fluctuations, so the high values, are going to be much larger. Yeah? So that's the kind of things that I'm having in mind. All right. Now, of course, once I've drawn these degrees, I can make a log-log plot of the degree sequence, and I get something like this. And this looks precisely like the plots I had for the degree sequences in the Internet Movie Database and the Autonomous Systems graph. Yeah? So in that sense, this is maybe doing the right thing. Now, I've now postulated what the size of the network is, and I've postulated what the degrees are, but that doesn't yet prove make a graph. In order to make a graph, you should actually connect you should actually form the edges. Yeah? And that's what the configuration model does. And that works best if I describe that on the board. Oh, that's interesting. So I'll do this in a very small example. I will just have a fixed number of vertices. Let's just stop at 5. And I visualize their degrees by just letting some stubs or half edges hang from those. So for example, if the degree of 1 would be 4, I would draw 4 of those. And there are 2, 1, 2, 3. Well, these should correspond to a degree sequence in my graph. So it better be the case that the sum of the degrees is even, because every edge is counted twice. This is sometimes called the handshake lemma. So is that the case here? Even, even, odd, even, odd? Yes. So I give this talk more often, and in about 50% of the cases it works, and otherwise it doesn't work. And if it doesn't work, I just add one extra half edge on the last vertex, and then it works. Okay, so now I've sort of visualized what my degree sequence is, and now I want to pair two of these half edges. That's how I can think of those, and that will form an edge. Yeah? Now I'm a probabilist, so the best way to do that is uniformly at random. So I just start here and say, okay, I want to connect this to one of the other half edges. Of course, I'm not allowed to attach it to itself. So let's say that I do it this way. And then for this one, I do the same. Whoop. And like that, and like that, and like that. And what have I done wrong? Oh, I've forgotten that one. Yeah? This doesn't look like a graph yet, but it helps to draw it in a more familiar form. And now let's draw the edges. 1 is connected to 4. 1 is connected to 2. 1 is connected to 3. And 1 is connected to 5. 2 is connected to 1, but I've already drawn that. 2 is connected to 5. 3 I already have. 4 is connected to 5. And that's it. So that's my graph. So this works really nicely. I get a nice graph for which the degree sequence is precisely how it should be. And in a certain sense, this is chance, because what could have been is that at the end I would be left with these two fellows that weren't paired, and then of course I would have only one chance, namely to connect them to one another. Then I would get this. Of course, it could also have been that this one had one more and this one had one more, and I would have connected those to one another. And then I would get this. Now that doesn't look like a graph yet. Now we get a multigraph. Now this is a potential problem, but as it turns out, this is not going to happen very often. So because it doesn't happen very often, and I'm thinking about giant graphs, I'm just going to ignore those. And you can do that in several ways. The easiest way is just close your eyes, and that means that we're actually rubbing them out. That has one drawback, and the drawback is that now the degree sequence is not precisely as it should be. Because I was saying that the degree of vertex 5 was 5, but now in reality the degree is only 3. So I've changed it a little bit. But if I don't do that too often, the characteristics are not really going to change. So that's one thing that I could do. The second thing that I could do is just ignore this and say, if I see a self loop like this, I don't like it, I just toss it away and try again. Of course, you could try that, and then it helps to know what the probability is that you'll succeed. I mean, if the probability that you're succeeding is extremely small, then you'll keep on throwing things away, and you'll actually never end up with something that is good. As it turns out, you don't. The probability of producing something right, under reasonable assumptions on the model, on the degrees, is strictly positive. Uniformly in the size of the graph. So it doesn't matter whether your graph has size 10 million, 10 billion, or 20. It will be uniformly positive. And that means that it'll just have to do a finite number of tries. And eventually I will actually get one that is simple. So simple here means no multiple graphs, no self-loops. Yeah? So for the remainder of the talk, I'll just ignore them. In fact, when I'm talking about distances, the double connections actually don't do anything. And the self-loops don't do anything either. So I might as well just ignore them, and which is what I will do. Now this is the description, but now in words on the transparency. So we assume that the total degree, which is the sum of the degrees, is even. Otherwise we're in trouble. We cannot pair them. And then we number them one by one, and we pair them uniformly at random. Now of course there's lots of things that you could complain about. Does anybody see something to complain about? Apart from the self-loops and the multiple edges? Well, it would not really be nice if the characteristics of the graph that you're producing would depend on the order in which you actually pair things. That would be bad. Now, the nice thing is that this sequence of pairing is what probabilists call an exchangeable sequence. And that means that the order doesn't matter. So it doesn't matter whether I order here from left to right, or from right to left, or whether I first do this one and then pair that one and then that one and that one. You always, in distribution, get the same result. That's nice. And in fact, this ordering could even be random, which is very nice, because maybe what I would like to do is somehow explore around the vertex. Then I'll first pair the ones, the half edges that are incident to the vertex, and then I'll find some new vertices, and then maybe I want to pair the half edges that are incident to that, and I want to explore in that way. It's something like breadth first search. But then you're actually doing it in a random order. That's even more tricky. But even that is allowed. You still get the same distribution. So that's actually quite nice. Yeah? So we've now produced a graph, and that's called the configuration model. And I mean, it's a bit of a strange name, configuration model. So Bolobashi invented this term, and what it boils down to is that you could, let's say, open up these vertices here and just draw the half edges. And then what you're doing is you're making a perfect matching of all of these half edges. And that's the configuration. And then you glue everything back together by realizing that these half edges are actually incident to a vertex, and that produces the graph. That's why this is called the configuration model. Any questions about this? Then I continue. So we'll be assuming that the degrees of these vertex are sufficiently nice, otherwise I will not be able to do asymptotics. And that just means that if I look at the empirical distribution of the degrees, that empirical distribution converges. And also the first moment and the second moment converge. And that is nice. And one way to achieve that is by taking these as realizations of IID random variables, and then all of these properties followed by the law of large numbers. So that's nice. But you can also find a deterministic way of producing such a graph sequence once you have sort of a target aim for your limiting distribution for the degrees. And here's a few properties. So there can be cycles of multiple edges, but they're very scarce. And if the second moment of the degrees converges to the limit of the second moment of the limiting degree distribution, then actually these numbers converge in distribution to Poisson variables with a finite mean. And they're independent. And therefore they take the value 0 with strictly positive probability. That's quite nice. So that allows this repetitive structure. You connect things. If you see self-loops or multiple edges, you toss it away. And if you don't, you keep it. And what is actually very nice about this is that the thing that you're keeping actually is a uniform random graph, simple random graph with the right degree sequence. So what is a uniform random graph with a certain degree sequence? Fix a degree sequence. If there's any graphs that has that degree sequence, you pick one of those uniformly at random. Now this seems a very simple procedure. But the drawback or the catch is that you need to know what all of them are. And actually there's a zillion of them. So how are you going to be able to find one uniformly at random? This is a difficulty. And this in fact is a difficulty in many combinatorial problems. You take something random out of a large set. If you cannot compute what that set is, you're in trouble. This gives you a very simple procedure of generating it by first taking the configuration model, conditioning that thing to be simple, which is the same thing as saying you take the first realization that is simple, and taking that. That actually is a uniform sample. Yeah? All right. The second model, inhomogeneous random graphs. Who of you have heard of the Erdős-Rényi random graph? Okay, that's a fair amount. So inhomogeneous random graphs you should really think of as being extensions of the Erdős-Rényi random graph. In the Erdős-Rényi random graph, what you do is you take the vertices 1 up to n, and you connect any any pair of them with equal probability independently of one another. The drawback of this is that every vertex plays the same role. And that's reflected in the fact that the limiting degree of any vertex is Poissonian. And a Poisson distribution has extremely thin tails. So you will never see this scale-free behavior in the degree sequence in an Erdős-Rényi random graph, because there's just not enough variability. I mean, somehow you should build into the model that there are these individuals that are special because they happen to be Barack Obama. And if you don't, you're just not going to create them by itself. And that's where the inhomogeneity comes from. So you're basically postulating that certain individuals have a higher chance of making connections to others, by, for example, giving them a weight. Now there's many versions of these models. And here again, this is the Erdős-Rényi random graph. I will give a precise definition on the next transparency. So again, the Erdős-Rényi random graph, you have n choose 2 edges on the complete graph, and each one of them you keep with a fixed probability p. And what we often do is we scale the p and we take it to be a constant over n. That means that the average degree per vertex is a constant. And that's what we observe in real-world networks. That's the reason why this is being done. Okay? So how can one change that? Well, first of all, there are tons of ways how you can do that, and let me just describe one. And this is actually a pretty nice way of generalizing. There are several ways that are actually nice, and they're nice for different reasons. So this is the idea. What we keep is that the edges are independent, but they're not the same. And not being the same means that for every vertex, we associate a weight to that vertex, and that weight is going to moderate how many neighbors it will have. Yeah? So that means that for a vertex I associate a weight wi to it, and then, as a function of these w's, I'm going to say that the edge between vertex I and vertex j is present, or it's occupied, with a probability that is the product of the weights at vertex I and at vertex j, properly normalized. And a convenient normalization is that you take the sum of the weights plus wi, wj. That's not the only thing you could do. You could also take this out, but then it's not obvious that your probability actually is a probability. It could actually be larger than 1. So that's a bit of a problem. That's why this actually works better. Yeah? Now, in most cases, these weights are going to be reasonable. So they're going to be relatively small. And this will actually grow with n, roughly linearly with n, because you're summing n objects. And in that case, we can actually take this out. Now, the interpretation of this wi is that it's very close to the expected degree of vertex I. So if you compute the expected degree of vertex I, how do you do that? So di is the degree of vertex I. Then we can actually write d of I is the sum over all j in 1 up to n, but only the ones unequal to I, because I don't allow for self-loops, of a Bernoulli variable with that success probability. Yeah? And all of these Bernoulli variables are independent because all of my edges are independent. So if I then take the expectation of di, well, because all of them, it's just a sum, so I just get the sum of j unequal to I of the expectation of iij. But that's the same thing as the expectation of a Bernoulli variable, and a Bernoulli variable takes the value 1 with probability pij and 0 with probability 1 minus pij, and the expectation of a Bernoulli variable is just pij. Okay? So if I compute that, I have to sum over j, but I keep I fixed. So what I get is the sum over j unequal to I, wi, wj over, well, the sum over k from 1 up to n wk, that's this ln, which is here, plus wi wj. Okay. Now I want to do asymptotics of this object. Okay, well, first of all, this will grow like n, so I'm just going to ignore that. Let's keep things simple. Now, also, this contains n minus 1 terms, and I'm actually forgetting about 1. Well, this 1 is not going to matter. Yeah, so let's change that to an approximation sign, and that is fine. And what we get here is that the wi can be put in front, and then I get a sum over the j of wj divided by a sum over k of wk, and that of course drops out, and you get wi. So the expected degree is very close to wi. So that's the interpretation of wi. And this actually means that if you take vertices with a very high degree, a very high weight, they will actually have lots of friends. Yeah? So by making these weights vary, you can produce a graph that has varying degrees. So you've lost the egalitarian nature of the graph, of the Erdős-Rényi-Random graph. Of course, you can get the Erdős-Rényi-Random graph back when you just take all these p's to be the same. And you can do that by taking them all to be this, and then you get precisely p is lambda over n. Is the definition of this model clear? All edges are independent, but the edge probabilities are different for different I and j. Okay. So there are related models. I was already mentioning that. You can also just take wi, wj divided by the sum of the weights, but that could actually be larger than 1, and therefore you have to take the minimum with 1. Otherwise, this is not a probability. And an alternative is to take pij to be 1 minus e to the power minus wi wj over ln. And all of these models are basically the same, because n is tending to infinity. And there's actually rigorous results that will tell you that these models are, as they call, asymptotically equivalent. So that means that the asymptotic probability of an event in one is roughly the same as the asymptotic probability of that same event in the other, under certain conditions on the w's. And these are actually relatively mild. All right. Now, as for the degrees, we're again going to postulate that these weights are sufficiently nice. Because, you know, if they're just jumping all over the place, I'm never going to be able to see some sort of nice pattern emerging from my random graph. So I want them to somehow be sufficiently stable. And that reminds you very much of what is happening in the Internet Movie Database. Also there we saw that the degree distribution was stabilizing. So as the network was growing in time, the degree distribution didn't really change. So if you want to see that kind of stable behavior, you have to put it into the model. Because if at, let's say, n is 100,000, you do one thing. For n is 100,001, you do something completely different. From n is 100,002, you do something else again. You're never going to be able to take a limit as n tends to infinity. Okay? So the question is, what is the right notion of stability? And that turns out to be that the empirical distribution of the weights converges. And that's formulated here. So this basically says that this distribution function, as n tends to infinity, approaches a limit. And this limit is then the limit that somehow describes the limiting graph, whatever that is. And we also want that the average weight converges. And this is the same thing as saying that this sum here actually grows like n times this expectation. So it really grows proportionally with n. And in some cases, we will also need that the second moment converges. Yeah? So this is stability. And again, here are two canonical ways how you can achieve that. We can take these weights to be IID random variables, and then all of these results will follow from the strong law of large numbers. Or you can take them deterministically in the appropriate way, and the appropriate way, if you want to have a distribution function f, is to take them to be 1 minus f inverse of I over n. That actually turns out to have the appropriate distribution. The reason is that if you take this function and you substitute in a uniform random variable, then you get a random variable that has distribution function f. That's one of these nice properties of distribution functions. Now if you look at this collection of points for various I, that actually is 1 over n, 2 over n, 3 over n, that actually approaches a uniform random variable. So it's like you're sticking in a uniform random variable, and therefore this distribution will actually converge to a random variable with the appropriate distribution function. That's basically the idea. Yeah? So one thing you can do is take this function to be a power law, and this would be one way of producing a power law. And then you can compute what this object is, and what you get is that Wj is a constant times n over j to a power, and this power is directly related to the power that you see here. And that's it. So this is the way how you can obtain power laws, by choosing these weights in the appropriate way. Of course, we've been interested in degrees. In my real-world networks, we've often plotted those degrees. So the question is, what happens to these degrees? Well, the main result here is that if you assume that this regularity condition for the weights hold, then actually, if you look at the proportion of vertices with degree k, that's what this is. So you sum out a 1 when the degree of the vertex I is k, and you sum out a 0 otherwise, and then you normalize it by n. So this is nothing but the proportion of vertices with degree k. So this pkn is actually a random probability distribution. And this random probability distribution describes precisely the degree of a uniformly chosen vertex in my network. Now it's random because my graph is a random graph, but it's still a probability distribution. So you take a vertex uniformly and random, and you inspect what its degree is. That's what it describes. And as it turns out, if we assume that this weight regularity holds, then this law will actually converge to a limiting distribution. So for every k, pkn, which is a random variable, converges in probability to some limiting value. That limiting value is not a random variable, it's a constant. And that constant turns out to be this value. And for those of you who know Poisson random variables, you will interpret this as being the probability that a Poisson random variable with a random parameter, which is described by W, takes on the value k. So if, in particular, if W is fixed, which corresponds to the Erdős-Rényi random graph, you just get a normal Poisson distribution. But if W varies, you get what is called a mixed Poisson random variable. And of course, if this W varies a great amount, then you will also get that the limiting degree distribution varies a great amount. And that's reflected in this. If you want to have a power law degree sequence, so that's the same thing as saying that the tail probability of the degrees, which is this, drops off like an inverse power of k, then you get that precisely when the W satisfy the same thing. And it's actually the same exponent. And it's even the same constant. So somehow these weights really describe, or the tail behavior of these weights really describe the tail behavior of your degrees. That's what you see. Any questions about this model? Edges are independent, and the weights are chosen different from one another in a stable way. That's the short summary. All right, yes?
Was there no limit on the second moment?
Excuse me?
It didn't have to be finite, the second moment.
In fact, that will enter, but not here. For this, it's perfectly fine if the second moment is finite, is infinite. But for later properties, that will be a deciding factor between different cases. Yeah. So here you only need that the first moment is finite. Other questions? All right. So I'm halfway. I'm not quite halfway yet. There's a third model that I would like to introduce. And that's the end then of my first lecture. I'm not entirely sure whether we should have a break or not, but I'll ask you again. So the third class of models that I would like to describe is what are called preferential attachment models. And these models are really different from the models that I've been discussing so far, because the models that I've been discussing so far have a size, and this size is fixed. I'm later sending the size to infinity, But as I change the size, my network changes, because my edge probabilities change. So I cannot really think of it as being a dynamic model. In the preferential attachment model, it really is a dynamic model to start with. So what you start with is a very simple model, for example, with one vertex or two vertices. And then you add vertices one by one, and you give them some rule for how they attach to the network that is there. And that depends on the network that is currently there. That is a dynamic model. And then what you're interested in is, well, what is the shape of this network going to be when the network grows to infinity? So it's more constructing a graph from first principles. Now, this paper really started the boom of network science. It's a paper by two physicists, Albert and Barabasi. Albert, at that moment, was a PhD student of Laszlo Barabasi. And this one has probably now 17,000 citations. So this is a number that is gigantic. It's one of the most highly cited papers in science, I would say. And they basically postulated a mechanism and investigated that on the non-rigorous basis, just simulations. And very close to that same time period, by four mathematicians, Bolobash, Reardon, Spencer, and Tusnadi. At that moment, Reardon was a PhD student of Bela Bolobash, really proved the asymptotic behavior within the model and showed that the degree sequence of this random graph process actually has some peculiar behavior, namely it's scale-free. So that's the whole importance of this idea. They've postulated a very simple mechanism that will produce scale-free behavior. In the configuration model, you sort of put in scale-free behavior, and then of course you get it, because you've put it in. Here it's not really explicitly being put in, but it comes out from somehow an underlying mechanism that produces it. That makes it interesting because it gives a possible reason why you see the scale-free behavior in real-world networks. Okay? So it's growing in time, and new vertices are more likely to connect to vertices that already have a high degree. So in a social network setting, you should think of a situation where you have individuals, and the socially active individuals, of course, have a high degree. They get to know many people, and because they're very socially active, if a new person arrives in the scene, they're more likely to get to know this socially active individual. That's the idea. So there's some preference here. That's what the preferential attachment refers to. So it's sometimes called the rich get richer model. If you're rich, socially rich in the sense that you have a high degree, you have lots of friends, you're more likely to become even richer. Well, maybe this is a phenomenon that we really see in society. In a certain sense, I actually find this name bad. Because if you look at the model, it's actually the old get richer model. Because those who were there the first, those are the ones that are rich. All right. So how does this go? As I was saying, it's a dynamic model. So it changes over time. And what happens is that at time n, you add a single vertex to the system. So at time n, the graph will consist of n vertices. So you should not really think of n as being calendar time, but somehow network growth time. And it has a fixed number of edges emanating from it. And I denote that by m. In fact, that's not so crucial. It could also have a random number of edges coming from it. That's not the main point. What is the main point is that it has these edges and it can connect those to the network that is there. And the question is, how does it do so? Well, first of all, it's going to do that in a random way, because this is a random graph model. But for every of these edges, what it will do is it will pick one of the vertices in the network with a probability that is proportional to the degree plus a constant. So those individuals that already have a high degree are more likely to be chosen, and therefore even get a higher degree. And there's a reinforcement scheme at play here. No? So in the original Albert and Barabasi model, this delta wasn't there. So they just did it proportionally to the degree. I'll try to convince you of the fact that it's actually good to have this delta there. Okay? So di of n is the degree of vertex I at time n. Of course, these degrees are changing over time. Because if a new vertex comes in and attaches to me, my degree goes up. So you really have to record the degrees at a given time, as time proceeds. And what turns out to happen is that this yields a power law degree sequence with an exponent that depends on all the parameters of the model, delta and m, and this exponent is 3 plus delta over m. And delta has to be larger than minus m, otherwise somehow the model doesn't make much sense. You get negative probabilities and we don't like that. So that's why we always say that delta has to be larger than minus m. So that means that this 3 plus delta over m can be any value that is larger than 2, strictly larger than 2. That means that you can produce dynamic random graph models for which you get scale-free behavior with an exponent that you can tune. And that depends on the precise attachment mechanism in a very sensitive way. Namely, it depends on this constant that you see here. Which may be a bit strange, right? Because in the end, you're going to have a graph with lots of vertices with extremely high degree. And if the degree is extremely high, it actually doesn't matter whether you have this delta or not. But the delta is important for the characteristics of the degree sequence because it changes the power law. So this is very subtle. There's a very subtle mechanism here. And this is what you get when you draw this, when you simulate this graph. This is a graph of size 1,000,000. We took delta is equal to 0 and m is equal to 2, and this is the degree sequence that you get. Now you'll be hard pressed to see that this is not a draw from an IID distribution with the same degree sequence. It's very difficult to see. It's not, because this really is the degree sequence of this graph. But okay. So what does this say? I mean, I haven't really stated a theorem here. And I was told to write there, so I'll try to stick to that. What does this mean? Well, it actually means something very similar to what we were writing down for the inhomogeneous random graph. Namely, if I look at the proportion of vertices at time n that have degree equal to k. And of course here I should bear in mind that the degree of a vertex is a dynamic quantity that grows in time. If I just look at the proportion of vertices that have degree k, then this object will converge in probability, even almost surely, to a limiting value, pk. And this pk has an asymptotic power law distribution. And in this case, what turns out to be the case is that as k tends to infinity, this behaves like k to the power minus tau. So if you draw this in a log-log plot, what you will see is a straight line, and in fact the slope will be minus tau. So in this case, delta is equal to 0, so tau is 3, the slope should be minus 3. I have a hard time seeing that, but that's what it is. Yeah? So the nice thing in this model is that the scale-free behavior is really produced by a rule that does not seem to explicitly incorporate the power law, and it seems to be a very reasonable rule. People with a higher degree are probably more likely to attract connections from other people. Nothing wrong with that. It's just that why it should be precisely this rule, that is not so clear. I mean, anything that is preferential, I mean, if you were to take the square here or the square root, that would still be preferential. There's no reason why an affine scheme, this is sometimes called an affine scheme, why that should be reasonable. But it is true that the affine scheme is the only one that produces a power law. So whether Albert and Barabasi were lucky or whether they had some deeper insight here, we don't know. So this is what Laszlo Barabasi says about this. I find this an amusing quote. The scale-free topology is evidence of organizing principles acting at each stage of the network formation. No matter how large and complex a network becomes, as long as preferential attachment and growth are present, it will maintain its hub-dominated scale-free topology. Now, this is false, because you only see scale-free behavior, oh, the wrong way. You only will see scale-free behavior when you take one of these affine schemes. If you take a square root, you actually get stretched exponential behavior, quite different. If you truncate this rule, let's say it's the degree up to degree 100,000, and then you stop it, then you will see a power law with an exponential cutoff. So it really depends very sensitively on the precise rule that you're taking here. So it's not just preferential behavior that is important, it's actually affine behavior that is important to get scale-free behavior. Yeah? All right, that was my first lecture.